Hello everyone and welcome to the Institute of Physics East Midlands Branch Featured Talk 2021. My name is Rebecca Dewey and I'm the chair of the branch committee. We organise these featured talks each year and we've recently hosted speakers such as theoretical physicist and science communicator Jim Al-Khalili, planetary scientist and aspiring astronaut Susie Imber, writer, comedian and broadcaster Tamandra Harkness, and lifelong contributor to the field of astrophysics, Professor Dame Jocelyn Bell-Burnell. We usually host our featured talks in person, touring around various parts of the East Midlands, but due to the obvious, our plans have somewhat changed this year. We're absolutely thrilled to be able to take advantage of the new situation and bring this lecture to so many more people, spanning a much wider geographical range, and all from the comfort of our and your own homes. The virtual nature of communications of late has also given us the opportunity to bring you speakers who are geographically nowhere near us, as we've done today. James Kakalios is a professor of physics at the University of Minnesota, known within the scientific community for his work with complex and disordered systems. He moonlights as an author, writing popular science books that explain physics principles in a fun, easy to understand, and often humorous manner. One of these books, The Physics of Superheroes, considers comic book superheroes from the standpoint of the fundamental laws of physics that govern the world around us. In 2009, James won an Emmy Award in the Upper Midwest region's Advanced Media Arts and Entertainment category for a University News Service YouTube video, The Science of Watchmen, outlining James's work as a science consultant for the Warner Brothers film Watchmen. So I'm super excited to be introducing James tonight to give his lecture entitled The Uncanny Physics of Superhero Comic Books. For anybody who'd like to receive this lecture in British Sign Language, we have a BSL interpreter for you tonight, Christopher Stone, signing for you this evening. You can click the View button at the top right-hand corner of the screen and select Side by Side Gallery, which will allow you to use the sliding bar to make Christopher and James bigger or smaller. If you choose Hide Non-Video Participants from the same menu, it'll also hide those empty boxes that we don't need. There will be an opportunity for me to read out some of your questions at the end, so please get those coming in the chat during the lecture. This lecture and BSL interpretation will be recorded and posted online for future access. Over to you, Jim.
Well, thank you very much. Thank you, Rebecca, and thank you, everyone, the IOP, for inviting me to give this talk. I wish I could be there in person, but alas, I cannot. So let me get into it right away and talk about the uncanny physics of superhero comic books. So let me begin by a little background of how did a mild-mannered physics professor become associated with Spider-Man and Superman. In my day job as a university professor, I do research in experimental condensed matter physics. Condensed matter is a fancy way of saying solid-state physics, and experimentalist obviously means that I work in a lab as opposed to doing theory. My research actually goes from the nano to the neuro. So we study nanocrystals of one type of semiconductor and embed them in an amorphous matrix of a different type of semiconductor in order to make new materials for solar cells or thin film transistors. And I have collaborations with professors in neuroscience where we use the techniques we developed to study electronic noise in disordered semiconductors and apply them to voltage fluctuations in the brain. But that's not why I'm here tonight. I'm here tonight because back in 2001, I created a seminar class at the University of Minnesota that was originally called Everything I Know About Science I Learned from Reading Comic Books, which my colleagues say explains a great deal. Now, this is a real physics class that covers everything from Isaac Newton to the transistor, but there's not an inclined plane or pulley in sight. Rather, all the examples come from superhero comic books, and as much as possible, those cases where the superheroes get their science right. Here's a comic, an old action comic, a comic of Superman that I bought back as a kid when it first came out in the 1960s for the grand total of 12 cents, which gives you a sense of my age, where Superman visited a college campus. And as a kid, I was very interested in what life in college was going to be like. And so I figured, hey, this is a good way to learn about that. Even as a kid, I knew that the stuff with Superman wasn't too accurate, but there were things in the comic book that did turn out to be a valid representation of life at university. Namely, all college professors at all times always wear caps and gowns, and all college professors are 800-year-old white men. So anyway, the class did very well. Seemed to be successful. And then in the spring of 2002, the first Spider-Man movie was about to open, the one with Tobey Maguire, directed by Sam Raimi. And I thought, well, this is a good opportunity to get some science into the newspaper. So I wrote an essay that was published in the Minneapolis Star-Tribune, my local newspaper, on how the death of Gwen Stacy, Spider-Man's girlfriend, in 1973, in, as you all know, Amazing Spider-Man number 121, turns out to be a textbook illustration of impulse and momentum. And they published this in the newspaper, and the university put out a little press release about me saying, well, Spider-Man's on the big screen, but if you want to know about the science of superheroes, the person to ask is Professor Jim Kakalios, teaches this freshman seminar, blah, blah, blah. The university has put out press releases about me before, about my work on 1/F noise and disordered semiconductors. Result? Zero. You write one story about Spider-Man, however. So the article was published on Friday. The Spider-Man movie opened on Friday. The press release went out on Friday. By Monday, I got calls from CNN, the BBC, the London Times, the Associated Press came to my office to do a story where I just happened to have these lecture demonstration tools on hand. That was a lucky break. You know, at this stage of my career, I've reconciled myself to the fact that I could win 3 Nobel Prizes, and I know what photo they're using in my obituary. I say this to my colleagues, and they say, win 3 Nobel Prizes how? Like in a crap game? This article actually went around the country. My sister-in-law gave me, this is a clipping that my sister-in-law sent me from the Chicago Sun-Times. And then we started appearing in places that, and then one of the graduate students brought back a clipping from Turkey, where I think I know what they're saying about me. And then I started appearing in places that physics professors don't usually show up. So, I mean, we've all been in lockdown here for the past year or so, and, you know, playing board games to kind of pass the time. And I'll tell you right now that if you ever wind up playing Trivial Pursuit and you have volume 6, I'll tell you now that if you get card 291, the science question, the answer is kryptons. The question is, what planet's gravity did science professor Jim Kakalios estimate by calculating the force needed to leap over an Earth building in a single bound? So I didn't even know about this, but so I show up here in the story. I didn't even know about this. One of the graduate students showed me the card. I borrowed it. I went down to the main office of the physics department. I saw my department chairman, and I showed him the card, and I said, Alan, who's the most famous scientist you know? And he looked at the card, and he looked at me, and he said, Stephen Hawking. I said, who's not a genius? Oh, well, then it's you. But this led me, one of the nice things about all this attention was the large number of emails I received from students and teachers and people long out of college who liked this idea of using superheroes to teach physics and asked if I had a book, which eventually led to my writing a book, The Physics of Superheroes, which led to another book, The Amazing Story of Quantum Mechanics, that addresses the question the fact that we were promised jetpacks and flying cars here in the future, 21st century. And what we got instead were laptop computers and smartphones. And then the most recent book just follows the physics of everyday life from the moment you get up in the morning to the end of the day, and explains the physics of all the technology that you interact with, from keyless entries to your toaster. Now, you're attending this talk, I'm giving this talk online due to the coronavirus. A significant portion of the population, certainly in the United States, is resisting taking the COVID vaccine, which jeopardizes herd immunity. There's been some active pushback against science and the results of scientific research, and don't get me started on climate change. And so I would maintain that science communication, education, outreach, and engagement with the public have never been more timely and more important. And if I can do it using superheroes, well, it wouldn't be the first time these heroes have saved the day. Now, my job is not to go around and analyze the superpowers and try to justify them using physics, because clearly they are physically impossible. And I don't see my job as being like Dr. No or Professor Grump saying, well, this could never happen, and this is impossible, and what's the deal with the Hulk's pants anyway? Unstable molecules. So what I'd rather do is grant each character a one-time miracle exemption from the laws of nature and say, well, if you were super strong, or could stretch like a rubber band, or could run at super speed like the Flash here, could you run across the ocean or up the side of a building, drag people behind you in your wake? All things that the character is shown doing in the comic books, all things that are correct from a physics point of view once you make the suspension of disbelief. Here we see the Flash, a DC comic superhero who has the ability to run super speed, and a crook is shooting at him, but the Flash is faster than a speeding bullet. But there are innocent bystanders in the way, and the Flash is not bulletproof. He's not invulnerable. He's just very fast. But we see with a sweeping motion, the Flash plucked the bullets, right out of the air before they could harm him. And there's an editor's note here. Flash's action in stopping the bullets is similar to that of a baseball fielder who stops a hot grounder by letting his glove travel momentarily in the same direction as the ball. And this is correct from a physics point of view. Back over a year ago, I picked up an object going 500 miles per hour when I poured myself some ginger ale on the airplane. It's going 500 miles per hour. I'm going 500 miles per hour. Not a problem. If I'm standing still and it's going 500 miles per hour, then I have a problem. So here we see some correct science in a Flash comic book. We get some other correct science in a Flash comic book. Here the Flash is trying to run at the speed of light. And he's finding that it is somewhat difficult. And we see the mighty monarch of motion pours it on. They always had these great alliterative nicknames for the Flash. He was the Scarlet Speedster, the Crimson Comet, the Viceroy of Velocity. And the Flash is thinking, it's taking me a little longer than usual to reach light velocity. I wonder if I'm tired or something that could affect my super speed. Good gosh, there's no doubt of it. I'm slowing down. I'm going slower and slower despite all my efforts. I can't go any faster because I'm getting heavier. Something's happening to me. Now, those who know Einstein's special theory of relativity know why the Flash is getting heavier as he tries to run at the speed of light. An alien is shooting him with a gravity increasing ray. But if you take it out of context, it's a perfect illustration of Einstein's theory. One last example with the Flash. I just love this one because it is so silly. Something has happened to the Flash, so he can't touch anyone without killing them. Okay, don't ask. Comics. And he wants to catch a bank robber, but he doesn't want to kill him. He just wants to subdue him so he can hand him over to the police. And so he runs a half mile away and he starts racing around a pear tree. And he's thinking, by setting up a current of air, I've shaken those pears off their branches. And then in the second panel, now by racing swiftly back to the car, I'll start a suction to draw the pears after me. And then I'll duck down, and the pairs traveling at high speed will do my job for me, thereby illustrating Newton's third law of motion, which is usually expressed as for every action, there's an equal and opposite reaction, or another way to put it, forces come in pairs. You know, you're all muted and I can't hear you, but I could hear you still groaning at that joke. And I have to remind you that I am a teacher. Therefore, your hatred only makes me stronger. So, I want to mention that superhero comic books and physics back in the 1960s, these are examples from what's called the Silver Age of comic books back in the 1960s. They had one thing in common: a lot of white men. Nowadays, now there is a belated and overdue growing effort to expand the talent pool in STEM fields: science, technology, engineering, mathematics. In addition to being the right thing to do, given the problems that we face and have to be addressed, we can't afford to ignore the contributions of anyone, and we need all the talent we can get. We find that comic books have been actually taking a similar attitude and have been stepping up to the plate as well. So if you go to the local comic book shop, you will find that Captain America is Sam Wilson. Thor is Jane Foster. Some of these have gone back to the original white male characters, but they're at least now into the rotation. We have Amadeus Cho as the Hulk, Riri Williams as Iron Man, Ms. Marvel is Kamala Khan, Spider-Man, Miles Morales. But of course, if you have a Spider-Man, you want to say, well, what about Squirrel Girl, the unbeatable Squirrel Girl? I really like Squirrel Girl. She's a great character. Her Doreen Green, and she has all the powers of a squirrel and all the powers of a girl. And she is a computer science major at a college, a university in, I think in Manhattan. Yeah, in Manhattan, in the Marvel Comics. And frequently, things that she learns in her computer science classes show up in her adventures, and she uses this knowledge to defeat whoever she's facing. And I love the comic, and I wrote to them and I said, I just want to point out that when you're in college and you say you're a computer science major, you don't take only computer science classes. You might take an English class, a history class, a physics class. And so they said, oh, this is a good point. Then a few months later, I got interviewed for a website to talk about the physics behind superheroes and superhero punching, whether they would fly backwards when they punched an object or a person, and so on and so forth. And then a few months later, in Squirrel Girl's physics class, they addressed the physics of punching. And Squirrel Girl said to her best friend that she wanted to ditch class to go out crime fighting, but she realized, offer rescinded. I forgot how physics is totally amazing. So hopefully I will give you a sense of how totally amazing physics is. Now, I've been mentioning just the characters from the pages of the comic book, but of course, there's also been some diversity that's now entered into the cinema as well. So we have the Black Panther, where we can talk about vibranium and conservation of energy issues. If it absorbs all vibrations, that energy has to go somewhere. And in the movies, it's being stored in little nanocells and then being able to be released. So there they get their physics right. We get Captain Marvel, and she gets her powers from the Tesseract, the Space Stone, and we can talk about symmetries of physics in this way. And of course, we have Diana Prince, we have Wonder Woman, and naturally enough, we can use Wonder Woman to talk about material science. In particular, let's talk about the material science of Wonder Woman's bracelets. So Wonder Woman actually has a variety of accoutrements that she uses to fight crime. She uses a lasso of truth, which if she wraps it around you, you are compelled to speak honestly and truthfully. And an interesting point is to note that Wonder Woman was created back in 1941 by a psychologist, Dr. William Moulton Marston, who is one of the co-inventors of the lie detector machine. So that's probably why she has a lasso of truth. She also has these bracelets that she's able to use to, with her Amazonian reflexes and strength, she's able to deflect bullets. But this is, of course, assuming that the bullets ricochet off the bracelets in the first place and don't penetrate through. And so what kind of material is this made out of? In the comics, it is said, well, it's very strong metal because it's Amazonian metal. But what would be the properties that we need for Amazonian metal for this to hold up? Well, we can analyze this from a physics point of view. We can look at the change in momentum that you would have when you deflect a bullet. A bullet comes in with a certain momentum and it comes out with, let's say, the same momentum but reverse direction. So there's a change in its momentum that way. And that can be accomplished by applying a force multiplied by the time that that force is active. And this is why we have airbags in our automobiles. You're going along at, say, 70 kilometers per hour, and you hit something and you keep going forward because an object in motion remains in motion until acted upon by an outside force. That outside force is coming up in a moment. It used to be provided by the steering column or the windshield. You're going to have a change of momentum. You're going, say, 70 kilometers per hour. You're going to stop. If the time is very short, the force needed is very large and would be oftentimes lethal. An airbag spreads the force over a larger area, so the pressure is reduced, and it deforms under contact. It's a little bit more giving than the steering column. And so the time increases, so the force necessary for the same change in momentum is reduced. So that's the physics of airbags, and it's the same physics we're going to apply to Wonder Woman's bracelets. Now we just have to plug in some numbers. We assume that there's a certain caliber of bullet, how much it weighs, how fast it's going. And we can calculate that if it ricochets in 1,000th of a second, then it exerts a force of 2,700 pounds over a very small area and results in a pressure of about 70,000 pounds per square inch onto the bracelet. And so you can ask, what kind of metal can withstand this pressure? And it turns out pretty much all of them. High-strength steel alloys can easily withstand well over 75,000 pounds per square inch. So to the answer to the question, what is Amazonian metal? Probably nothing more exotic than cold-rolled steel. But it's good from our point of view that it's not just the metal, but also her strength of her wrists and her reflexes that enable her to do this. So it's a good thing that she's fighting on our side. Spider-Man. Let's talk about Spider-Man. And again, staying with the material science point of view a little bit, let's talk at some of his powers. He has wall crawling and web swinging. Let's start with the wall crawling. Spider-Man clings to walls, any surface, and there's actual real-world examples of this. For example, gecko lizards that can easily climb up vertical surfaces across the ceiling. How does a gecko lizard do it? They use static cling. They use, basically they use electrostatics. If you look at a gecko's foot and you look at one of its toes, I guess, and there's a series of pads. And then if you zoom in on those pads, you find millions of microscopic fibers in each little pad on the gecko's toe and over the entire hand. What does that do? There's a very weak, so the gecko uses static cling to adhere to a wall. But it's not as if the gecko is like rubbing its feet across a shag carpeting to build up a charge and then puts his foot on the wall. How does it do this without building up, having a charge naturally? It uses something called the van der Waals effect, so that if you have a fiber and it's got atoms in it, and there are electric charges around each of the atoms. And if it comes near a surface, there are going to be momentary fluctuations in charge along the fiber. One region might be momentarily have a little bit, be more positive than the surrounding regions. Another region might be a little bit more negative than its neighboring regions. This negative charge would induce a positive charge in the wall. This positive charge would induce a negative charge. And since opposite charges attract, there would be an attractive force. This is a very weak force because it's due to just fluctuations. If this positive charge fluctuated over to a negative charge, well, the negative charge would then induce a positive charge. So the attraction would still be there, but this is not due to real charges built up on the fiber, just fluctuations in the fiber that induce opposite fluctuations in the wall. This is a very weak force, and it dies off as 1 over the separation distance to the 6th power. So that means that if you increase the spacing by a factor of 10, the force goes down by a factor of 1,000,000. So it's a very weak force and it's very short range. This is why the fibers have to be microscopic, because a microscopic fiber has a large surface to volume ratio. So you can get it very close to the wall. And this is why you need millions of them, because it's a very weak force. This is how a gecko lizard does it. And this may be someday how we do it, because scientists are developing gecko tape, artificial tape that is manufactured to have millions of these little microscopic fibers. And in the first paper that was published, this is from a scientific paper in Nature Materials, where they demonstrated this tape by having a Spider-Man action figure adhere to a surface, to a ceiling, and it's not glued on or not using sticky tape, scotch tape like we're used to. It's using this gecko tape. And there are major barriers to being able to scale this up so that it could support the weight of a person, not just an action figure or not just a gecko lizard. But scientists are working on this. And if they ever do manage to make a tape that can hold up gloves, gecko gloves, that could hold up a person's weight, I'm making this promise right now in public. I'm never waiting for the elevator again. So we had wall crawling. Let's look at Spider-Man's web swinging. So Spider-Man, originally in the comic books, makes a technological web shooter. He creates a fluid that generates a webbing that can be shot out through a nozzle. And this has a great deal of strength. And if it's anything like real spider silk, then it will indeed be extremely strong. Real spider silk, real spider webbing is pound for pound stronger than steel cable and is stretchier, more elastic than nylon. It achieves this by having the strength and rigidity comes from having little rigid nanocrystals within the webbing that are attached to each other by little stretchy polymers that provide the elasticity. And the whole thing is in a tube that's filled with fluid that uniformly distributes the force over the length of the webbing. Scientists would dearly love to be able to manufacture this artificially. Then you'd be able to have lightweight clothing that would be stronger than Kevlar. How strong is Spider-Man's webbing? Well, the way you determine strength of webbing in a material science laboratory would be to keep adding stress until the material fails. So here I have an example from the second Spider-Man movie in 2004, where Spider-Man needs to stop a runaway elevator train. And there we go. You know what? It just occurred to me that this may not be showing. I might have to change this. Let's go back and start this up because this was not embedded properly in my, here we go. It just occurred to me that you may not be able to be seeing that. There you go. Here we go. By the way, I see that look a lot in class. Okay. Let me go back to the PowerPoint. Good. So there we go. From that scene, we can determine the tensile strength of Spider-Man's webbing. We can estimate the diameter of the webbing. We can count the number of web lines. We can look up the mass of the train. We can determine its initial velocity by looking at how long it takes to pass like a city block. We know its final velocity. It comes to rest, stops. So we know the change in momentum. We know the time by which it takes to stop the car, the train. We then can determine the force necessary to stop it, looking at the distance over which the webbing stretches before it stops. And we conclude that the webbing has to have a tensile strength of about 1,000 megapascal, which is 145,000 pounds per square inch. Now, steel has a strength of 250 to 500 megapascal, but spider silk has a tensile strength of 1,200 megapascals, which just goes to prove that they couldn't put it in a movie if it wasn't true. Now, as strong as spider silk is, it comes nowhere close to the record for tensile strengths, which is held by carbon nanotubes, which has a tensile strength of 60,000 megapascals. And since this is actually something related to carbon nanotubes is in the news a fair amount, I'll take a minute to talk about this. So, a key thing is that not all carbon solids are created equal. You could have carbon arranged in a tetrahedral arrangement, in which case you would have diamond. Or you could have the carbon arranged in two-dimensional sheets, in which case you would have graphite. And graphite is the material that is used in pencils for writing. The bonds between the carbon atoms are in the sheet, in this green sheet, say, are very, very strong. They're actually stronger. The carbon-carbon bonds here are actually stronger than the carbon-carbon bonds in diamond. The bonds between the sheets are extremely weak. And that's why it's good for writing. Because you have a pencil lead, you have the graphite, and you push it against a piece of paper, and you're unpeeling the solid graphite layer by layer. And depending on how hard or soft you push, determines how many layers get peeled off. And then it's held onto the piece of paper by electrostatic attraction, which is why it's easy to rub it off with an eraser when you want to change what you wrote. But say I take a single, and here's an electron microscope, excuse me, not an electron microscope, a scanning tunneling microscope, which was developed back in the mid-1980s, that can image individual atoms. And here we're looking at the surface of graphite, and each one of these white dots is an individual carbon atom, and we can see them arranged in a hexagonal structure. As I said, if you have multiple layers of these carbon sheets, we call that graphite. If you had a single sheet, you were able to peel off a single sheet of this carbon, of this plane, you would call it graphene. Graphene was first fabricated back in, well, just a little over 10 years ago. Well, about 15 years ago. Andre Gein took a piece of graphite and he put some Scotch tape on it and he pulled it off and he split the material. Then he put some more Scotch tape, pulled it off, more Scotch tape, pulled it off, and kept going until he got to the stage where he had one single sheet, one single layer, atomic layer of graphene. Graphene is extremely strong. If you had a sheet of paper and held it up, it would just bend under its own weight. Graphene would stay solid and rigid. It would not bend under its own weight. Even if you had two people standing on the other end, it would not deflect. So, and since it's only one atom thick, 97% of the light passes through it. So it's kind of a good thing to build Wonder Woman's invisible plane out of, strong and transparent. If you take graphene and you roll it up into a cylinder, you have something that's called a carbon nanotube. And so this is only about maybe 3 atoms or so across. And it's extremely strong because all of these bonds are these graphitic-like bonds that are stronger than diamond. So that if you were to take a carbon nanotubes and braid them into a cable, a fiber, spider web, if you will, then a fiber that is no thicker than this period here, this little dot, which is smaller than the dot of the laser pointer, would be able to hold up 2 sports utility vehicles, two heavy-duty, fully loaded automobiles, just from that tiny little fiber. In the Spider-Man, the Tobey Maguire clip that I showed, Spider-Man's webbing was organic. It just came out of his wrist. In the latest versions of Spider-Man movie with Tom Holland, he's back to making technological web shooters and technological webbing in his chemistry lab. And we see here his chemistry notes, and he looks like he's working on graphitic carbon and seeing if he can make it into a webbing and a web fluid, which looks like he is because he's able to hold together a ferry boat that had been split in half by the Vulture because of comic book movies. And the question is, could you make carbon nanotube fibers in bulk like that? Up until very recently, this was completely the realm of fantasy. But more recently, scientists such as University of Cincinnati professor Veselin Chanov had been able to grow what's called carbon nanotubes to scale, making mass quantities of it and being able to braid them into fibers and into threads. In some cases, 50 yards, roughly 50 meters long of braided carbon nanotubes. So here again, we have something that was purely in the realm of comic books and is being developed and getting closer to reality. looking to see how I'm doing on time. So there's another shot of that. I think that's amazing, just amazing. So let's talk a little bit more about graphene. The 1 atomic layer thick, extremely strong material. A few years back, Iron Man was going through some things and he changed his red and gold suit of armor for something that looks like he stepped out of the Genius Bar at the local Apple store. Maybe that's what he was going for. But he also modified his helmet so that his adoring public could see his face. But of course, leaving your face unprotected like that has its downsides. Like when someone walks up to him and tries to shoot him point blank in the face. But it turns out that Tony Stark was unharmed. And the shooter is amazed, and he explains, it's called graphene, stronger than most steels, transparent. Well, I've already explained, it would be transparent, would be invisible, because it's only 1 atom thick. And it is stronger than most steels. But is it really bulletproof? Well, in one of these really amusing coincidences, the very week that issue of Spider-Man came out in local comic book shops, another magazine landed on my desk that also contains fantastic stories and just breathtaking advances, Science Magazine. And here we see an article, even highlighted on the cover, shooting bullets through graphene sheets. And it has a less attractive title than something in the superior Spider-Man, Iron Man, but dynamical mechanical behavior of multi-layer graphene via supersonic projectile penetration. Basically, they took graphene and they shot little quartz pellets at it, little nano pellets at high velocities, and determined how much energy it takes to penetrate through the graphene. There was actually several layers of the graphene that they were using. And when you look at this, you see this is the amount of energy you need to penetrate through an object versus the velocity of the projectile. And here are most metals, steel, aluminum. This is Kevlar. Kevlar is very strong compared to, say, steel. This is graphene up here. Graphene is stronger than Kevlar, much, much stronger than steel. So Iron Man spoke the truth. Transparent, stronger than steel, bulletproof compared to steel, say. I figured that this was a coincidence too good to pass up, was a great opportunity for a little science outreach. So I wrote an article for Wired.com about the magical bulletproof material that made Iron Man give up iron, and talked about, basically gave me an excuse to write a story about graphene. And, there's, at the end of this online article, there's comments, of course. There's always comments. And usually people say, don't read the comments. Don't ever look at the comments. But here the comments were a treat. One person posed the question then, what's protecting his hair then? And before I could log on and put forward my hypothesis, someone else replied with the perfect answer. Brill cream, stopping bullets since 1928. Right? When the man's right, he's right. So what determines the strength of materials? I've talked about the chemistry, the bonding of the atoms, carbon atoms, and you could have two materials made out of carbon, and in one case you've got a rigid nanocrystal. In other cases, you could have carbon atoms in a stretchy polymer that's very elastic. Different properties, just depending on how you arrange the atoms in the material. But geometry also plays an important role. And so to illustrate that, I just want to talk about Gormu and the square cube law. So this goes back to a story that was in Fantastic Four number 271 back in the 1980s that took place before the Fantastic Four gained their powers, and Earth was threatened by this giant monster Gormu from another planet. And this, in the 1980s, was basically a tip of the hat, a callback to the comic books that Marvel was publishing before they published superhero comic books, before the Fantastic Four, before Spider-Man. They put out comics like Tales to Astonish or Journey into Mystery. And here, for example, I challenged Groot, the monster from Planet X. This is the same Groot that would go on to be a member of the Guardians of the Galaxy. And when he first appeared, he was trying to take over the planet. And this happened every issue, month after month. Earth was trying to be taken over by some sort of giant monster, and the police couldn't handle it. The military were helpless, and Earth would be doomed if not for the efforts of one lone scientist who would figure out the one weakness of these monstrous invaders and use that to vanquish them. Here we see, so this is Tales to Astonish from 1961. Groot. This is the cover. This is the very last panel in that story. The sheriff is saying, well, I never even thought of that. And the townsperson says, that's why Evans is a scientist and you're only a sheriff. And Evans' wife hugs him and says, oh, darling, forgive me. I've been such a fool. I'll never complain about you again. Never. And personally, I can't tell you how often I hear this in my own household. I can't tell you because it involves imaginary numbers, but it's a good thing that the scientists were on the case, because if they didn't have to deal with Groot, they had to contend with Lokar or Orgo or Mumba or Rambu or Gruto or Brutu or Gugam, son of Goom, or Fin Fang Foom, all of which pale against the most terrifying monster of all, the tax collector from outer space. But getting back to Gormu, in this story, Gormu's competitive advantage in the world-conquering business is that if you strike him with any form of energy, a bullet, a bomb, any type of weapon blast, he gets bigger. So every time you hit him, he gets bigger. How do you stop someone that every time you strike them grows and becomes even more formidable? Well, the scientist, Reed Richards, has an idea. And he goes back to where Gormu's ship first landed, and he does a measurement to confirm his hypothesis. And he concludes that the only way to stop Gormu is to continuously bombard him with energy. And at first, Gormu thinks it's a weapon, but then he realizes that it's a power beam. Yes, give me more power. But then he senses, wait, something is wrong. The power surges within me, but I do not grow stronger. I grow weaker. I am almost as big as the planet, yet I do no damage. It is as if I am no more than a phantom. What is happening to me? I am defeated. No. What Reed Richards realized that Gormu was growing at constant mass, not constant density. He hypothesized this and verified it by realizing that Gormu's footprints were getting bigger, but they were not getting deeper. And he realized that Gormu was not gaining mass or weight, he was just inflating. Now Gormu, the infinite monster, has become truly infinite. And Sue Storm says, "Oh, Reed, darling, I'll never doubt you again." But this gets to the heart of the cube square law. Density is mass over volume, which means that if I multiply volume by both sides, I can write mass is density times volume. So if your mass increases with your volume, then you are growing at constant density. But if you grow at constant mass, then as your volume goes up, your density has to go down by the same amount. And how much, if you increased at constant density, how much the mass would go up is reflected in what's called the cube law. So that if you have a cube that has a length, a side, each side is a length 1, and you make it 3 times bigger, you have 3 times 3 times 3, or 27 times as many cubes. And as each cube has the same density, then you have 27 times the mass. But the strength of materials, such as like muscles in your arms and your bones, are not determined by how long they are, but by how thick they are, right? So that strength is determined by the cross-sectional area. So if you increase by a factor of 3, the area only increases by 3 times 3, by 9, but the mass increased by 27. And so if you were to grow, if you had an expanding ray that could make you grow, as you got larger and larger, if you grew at constant density, you would become heavier and heavier. Your bones would become heavier and thicker and stronger, but not fast enough. And you would reach a point where you would break your legs, break your back by just standing up if you became too large. Another way to think about this is if you have a fishing line that's rated for 20 pounds and you want to hold up a 40-pound fish, you got to get a new fishing line. You don't make the line longer, you make it thicker in order to hold up the fish. As also explained in Squirrel Girl's physics class. Put another way, make yourself 10 times larger, your muscles get 100 times as big, but you have to carry 1,000 times more weight. That's why elephants look like elephants and not giant mice. You can't just scale up animals and expect them to work. I drew them for you because I am a good professor. And now, if I want to be a good professor, I better stop right now before I overstay my welcome. And so I just want to thank you and remind you that with physics comes both great power and great responsibility. Thank you all very much.
Thank you so much, James. That was an amazing talk. Really, really exciting. I really enjoyed listening to that.
Thank you.
So I want to remind everyone that this is an opportunity to ask any of those questions that you've always been wondering about any of James's work, about the physics of superheroes, and specifically about any of the talk today. And can I quickly invite David on while your questions are all filtering through? Just going to invite David on for a quick presentation.
It's like appearing Eurovision this weekend. It's like appearing next to the Macedonian entry, North Macedonian. We've got to use the right term. Anyway, so it's traditional for us to. I'm David, by the way. I'm the Midlands Regional Manager of the Institute of Physics. It's traditional for us to give a little gift. Obviously, I only got it on Monday, so it's actually been from a shop that's been closed.
Oh, thank you. Oh.
It's been from a shop that is currently closed and has been closed for the entire year, but I managed to track down the manager of the shop and convince her to go in and sell this to me. So it arrived on Monday. East Midlands is often the overlooked region of England. As a proud Middle Easterner, East Midlander myself, I'm happy to say that. But our greatest physics export is, of course, Sir Isaac Newton, who came from Lincolnshire. And he grew up at Woolsthorpe Manor, in the grounds of which is an apple tree. And I have managed to get hold of a pair of cufflinks with a little ring from the apple tree that Newton observed the falling apple on. So some point, if not in public, obviously, but if you could give me your address, I will send that over to you as a thank you for the fantastic lecture that we've
Don't move, I'm coming right there.
Oh, right. Okay. That's right. Well, actually, I live next to East Midlands Airport, so I'll just throw it up as a DHL plane as it flies over.
Oh,
and I'm sure.
I can't tell you how happy that makes me, how touched I am. I had the honor of visiting University of Lincoln, and we visited Newton's home, and I saw this apple tree, and I had all these pictures, and I saw like there's like an integral sign that's outside the house, and I saw, you know, how he didn't make his bed either, like all us great geniuses. And I desperately wanted a pair of those cufflinks, and they didn't have them. And Andre, I know that you were involved in this, and I want to thank you also. He's off there muted somewhere, but oh boy, you guys, thank you very much.
There's Andre.
That is much better than the standard coffee mug that I get. I have to say, that's wonderful. Thank you so much.
I'm also looking forward to filling in the customs declaration on it, so that'll be good as well. Okay, I'll leave you to the questions. Thank you.
Okay.
Okay, so we've got loads of questions coming in. Some of them are short questions, some of them long questions, and I'm going to like tie a few together so that I can sort of put a few to you at once. So this is something that actually I was thinking about throughout your talk. That we've been talking about the physics of superheroes throughout, and one of the audience has commented, one of Dan Dare's opponents has a small robotic bird that followed him everywhere and whose only function was to bolster his ego by encouragement and flattery. And I wondered, and I was looking at all of the frames from the comic books where the superheroes have these absolutely wrought in agony faces, and perhaps there is space for some psychology of superheroes. What do you think?
Yes. Well, now Dan Dare is British, if I remember correctly. So I'm actually very impressed with that it's a positive reinforcing. You would imagine that the Roman bird would be there saying like, all fame is fleeting, and giving them negative. Yeah, that would be certainly the technology of small flying drones that could have some artificial intelligence, some robotics. Of course, the smaller you make it, the lighter it becomes. And so then the easier it is to lift off. I mean, there's a tremendous amount that's coming in the next 10 years. There's a colleague of mine, Paul McEwen at Cornell University, and he's working with a large team. They're making microscopic, like nanobots, like microscopic robots, where on the one level you say, oh, what could go wrong? But there are applications of this, not just to provide ego boosts, but for, say, microscopic surgeries or drug deliveries or other types of processes. People are now using drones, searching in tiny spaces to search for survivors of, say, earthquakes or other catastrophes. So our understanding of this and how to make these things smaller and still active and still working and communicating via Bluetooth or other things, that was going to have what was science fiction in the 20th century, some of this is going to become science fact in the 21st.
That's super exciting, and a beautifully altruistic answer as well, just so lovely. So I've got another question from an audience member here. While the material science might allow superheroes to produce super materials, but perhaps the weak point would be their body. How would they protect their own flesh from dismantling under all this pressure?
So, you know, the thing is that we can survive I mean, you're talking about excess pressure, and that's obviously a good point. evolved in Earth gravity, and we evolved to take certain amounts of strains. Our bones, by the way, our skeleton structure is adapted to support our weight, but there's a great deal of redundancy built into it, because if you're jumping from a moderate height, you don't always break your legs as soon as you land. That there's a little bit of, there's some strength, there's some redundancy built into our bones. The point is that if you grow too large, you your weight increases faster than that redundancy, that strength can improve. Yes, there is this support, there's a certain amount that we can survive. And then there's a point where you enter into fantasy world, where you have to say, well, someone is like extremely strong or something else, so that they can, so it's not just the material science, but it's the body that's the limiting point, the weak link there. But when you mention pressure, we not only evolved in Earth's gravity, but in Earth's atmosphere. So you right now, every time you stand up, you're fighting against a force of 15 pounds per square inch. It's basically kind of equivalent to having, roughly a meter stick of lead pressing down on you. It would be if the atmosphere were doubled. We're at the bottom of the ocean, but it's an ocean of air. And since we evolved in this, we don't notice it because we were able to this was the conditions under which we developed. You're in outer space, you're an astronaut. You need to have that pressure on you still. If you were to take your helmet off, take your clothes off, you would have explosive decompression. The astronaut suits are big and bulky because they're trying to contain that much atmosphere within the suit to maintain the pressure that our bodies need to hold us together inside the suit. How do you make the suit smaller? You need to make them more skin tight and press with a greater pressure on the person. The problem is getting those on. In order to mimic the pressure, having a suit, an astronaut spacesuit that would mimic the pressures of Earth's atmosphere, it would have to be 10 times more compression than a compression sock, say, if you ever had one of those orthopedic socks. And you know that those are not cake to get on. And so what do you do there? And scientists are working on materials that are loose, and then you run an electric current through them and they tighten up. And so they'd be lightweight, loose to put on, and then you run a charge through them and they would tighten up and create a pressure on you that you would feel kind of squeezed when you're in atmospheric pressure, but when you're in outer space, you would say, okay, this is good, because it would keep you, and it would not be a big bulky suit, it would be a skin tight suit. And these are called shape memory materials that change their shape depending on like a temperature or a squeeze or twist. Shrink wrap, you put it as cellophane, you put it around lightly, loosely around an object, you heat it up and it shrinks and then forms a tight seal around whatever it's wrapped around. So these things exist, they're being developed for other applications, all trying to use our understanding of the world to solve. Science answers questions, engineering solves problems. And the two of them have to go hand in hand, and it leads to the lifestyle that we have today.
Brilliant, thank you. So I've got a few questions here from the audience on the general theme of scaling things up. So talking about the critical issues that need to be tackled before you can scale something up. And one audience member has asked, could a flea truly jump over a house if it was scaled up to the size of a man? So
that is a great question. That is a great question. A man is, say, 2 meters high, 2 meters tall, And best case scenario, they can leap 1 meter, just round numbers, okay? A flea is a few millimeters. And so that is, say it's 2 millimeters, so that's a factor of 1,000. So could it leap, and it can leap just like a man, 1 meter. It's not the relative sizes that determines it, but it's actually, you're going from the ground up into the air, and so you've changed your gravitational potential energy, and you do that by exerting a force down on the ground, pressing down on the ground, and the ground presses back on you through a process that physicists call jumping. And so you press down on the ground and the ground pushes back on you and you leap up in the air. We have much stronger muscles than a flea, but we have to lift a much larger mass. The flea has much weaker muscles, and actually it's not even muscles, it's kind of like springs in the exoskeleton, but it has to lift a much smaller mass. And the two of those just balance out, and basically a flea and a human can leap the same amount, 1 meter.
So if we were to scale up the size of the flea,
no, it would, well, then it would presumably, if it's growing at constant density, it gets heavier. And so it could exert a larger force, but it has to now lift a larger mass. See, in the Spider-Man comics, they said, oh, well, if spiders can jump this great distance, Spider-Man gets bitten by a radioactive spider, which I do not recommend, by the way. And so maybe he can leap like to the top of a building or something like that. And it's a standard, it's a common misconception that it's the geometric ratios that are important as opposed to the absolute heights. It's actually the absolute height that is the relevant factor.
Brilliant, thank you.
Sorry, I mean, it's kind of a bummer, but
we've still got to deal with physics. So we've got a question here from John, one of our committee members here. Is a space elevator using carbon nanotubes possible?
If you built it, this is what I would use for the cable, absolutely. And this is exactly, so there's this issue of a space elevator of basically, having, you could actually you don't even have to attach it to anything. You could just use, if it's at the right height, it's going to stay above the Earth as it rotates around, because it has to be quite high up. But then one thing goes down, the other car goes up, and you could lift objects. Most of the effort in space travel is getting out of Earth's immediate gravitational pull. And so if you could use a space elevator to lift objects up, you need much less fuel then to, say, go to the moon or Mars or what have you. Yeah, so yes, carbon nanotubes would be material number one that you would use. Now, they've been able to get it maybe 50 meters long. So we only have about another 10,000 kilometers to go. 10,999 minus 50. So, but we're working on it.
To do some work, yeah.
Yeah.
Or material science. So got another question here from Adrian. How does the Winter Soldier combine the strength of his arm to his body?
Oh, that's a great question. Right. So you see this a lot in, there's cyborgs. There are human cybernetic, amalgams. And that is a huge suspension of disbelief because you have something that is heavy and strong, and somehow it's being attached via tendons and muscles that are not able to take that strength, not able to take that weight. So basically, this is one of those miracle exemptions from the laws of nature that you have to invoke if you're going to have the story at all. People ask me about, do I go to the movies and you know, look for mistakes? And it's not like I sit there, you know, with a pad of paper and my calculator and say, ooh, my physics sense is tingling. It's, you know, I'm a fan and I want to enjoy it. But if you find something where they get it right, or they at least acknowledge, you know, that this is something unphysical, it's like catching a little Easter egg, catching a little hidden gem. And now I can say, ooh, I can use that. I must be a genius because I figured out how to get comic books and go to these movies on opening weekend is now part of my job description. So.
Brilliant. No, that's really lovely that actually we can pass on that message that you are there to enjoy the films, and that actually you're enjoying that you can use physics to understand them. I think
right. It's you know, the little bit of consulting I've done, and this has been consulting through the National Academy of Sciences on it's a volunteer basis. They probably throw away more on a week's worth of catering than they could to just give me any. But anyway. They want to get the science in these movies right enough. They don't need to get it right. They just need to get it right enough that you don't notice it. Because any moment where you're questioning what you see on the screen is a moment when you're not paying attention to the story. So we talk to them about how to make it, you know, somewhat plausible, how to make it somewhat that it's not egregious, that you see what's going on.
Yeah, that's so true. Such a good thing to strive for. So I've got another question here. How could Wanda project a force field the size of a village? Wanda from WandaVision. Yes, the Scarlet Witch, Wanda Maximoff.
Comics. It's just, yeah, that's just like, that's part of her power set, you know, presumably. It's, you know, one of the things that was initially, when the character first appeared, she had what was called Hex Powers. And the idea was that she could alter the probabilities of events. And so that if something had a 1 in a million chance of happening, if she used her powers, it would happen, you know? And so it wouldn't necessarily violate any laws of physics. It would just be very unlikely. And she could make the unlikely likely. And that, you could use that as a way of talking about real issues in physics, in what's called statistical mechanics. And when you deal with things like entropy and randomness, and say, what's to stop all the air molecules from just due to random collisions going over to one side of the room? And I'm sitting in the wrong side of the room and suddenly I suffocate. And there's a very good thing that stops. I mean, what stops that? Nothing. It could happen. It's just that the number of ways that could happen versus the number of ways where they could collide and stay spread out over the room that's such a large ratio that you would have to wait several times the age of the universe and you would still never see something like this happening. So it gives you this. So in some cases we deal with probabilities like Wanda Maximoff does, but we gain an understanding of how we can make predictions about things that are still probabilistic, because we don't have to worry about, you know, because the numbers are so large that you would never have to worry about seeing significant deviations from it. How she does this with a force field around the size of a village is, oh, I know how it's done. Special effects.
Sometimes that is the answer. It's the easiest way.
98% of the time is the answer.
Okay, we can probably squeeze in 1 or 2 more questions, but let's keep the answers relatively rapid.
Okay, okay, that was a shot at me. Okay, I heard.
No, it's not at all. No, I'm giving you an idea how enthusiastic your audience is. So, how would Aquaman speak or communicate underwater?
Telepathically. So he's actually not talking, but so when you think there are electric ionic currents in your brain going from neuron to neuron through synaptic junctions. Every time an electrical current changes direction, that's called an acceleration. And an accelerating electric charge creates an electromagnetic wave. And when you're thinking, you're generating electromagnetic waves that are basically like radio waves, but they're a billion times weaker than the radio waves that are around us right now that we use for our Wi-Fi and our smartphones and what have you, our radios. Some fish, like sharks, have they have an extra organ that can detect these electric fields due to other fish. And they use this in hunting prey. And these organs that the sharks have, for example, are so sensitive to changes in electric field that if you had a 9-volt battery and you connected one wire in Boston Harbor, and the other wire off of the coast of Miami in Florida, it would detect that electric field that's generated by that 9-volt battery. So if Aquaman has the similar organs, he could use and detect telepathically. And I know I want to keep it short, but I got to tell you this. There are scientists, Professor Bin He, used to be at Minnesota, now he's at Carnegie Mellon University, that are developing cybernetic helmets that can detect people's thoughts and send it via Bluetooth to a computer terminal. And they can do things like they can maneuver a remote controlled helicopter through an obstacle course by thinking which way they want it to go. And they're using this to develop prosthetics and treat paralysis. But this is also what you have in an Iron Man suit. He doesn't press a button or give a voice command. He thinks of something and it happens. And the comics say it's because he has a cybernetic helmet. That stuff is coming, believe it or not. So from Aquaman to Iron Man to us, this is our superpower right here.
Brilliant. Oh, that's really good. In fact, I think we should just leave it there because that's just
I was just thinking, boy, if she doesn't go out on that line, I don't know.
We'll go out on that line. That was a beautiful ending. Thank you so much, James, for such a really exciting talk and a really engaging discussion.
A huge pleasure. Thank you very much. An honor and a pleasure.
Thank you.